Yeah, that's good, Mateo. I get
Yeah,
it.
so just so you can, so basically we've
It's
got it
actually
set
to
up.
scale almost, really, at 48.
Yeah, it's pretty close. I mean, it's just, and it's scaled so that it kind of fits on a screen or a piece of paper if we print it, but we can obviously, it's going to depend on the conditions, but
So those are the 10-foot blades, Mateo?
yeah, those are 10-foot blades. Yeah.
We only see two because it's just the way you've made
I've
it.
got I'm looking at a section. So
Oh, yeah, right.
if it's out in the open, it kind of looks like a really nice green on a golf course. Like
So
with the
Andrea,
shape.
it's basically like an airfoil, right? And no
Correct.
matter which way the wind goes, I asked this question, it's going to go. Well, you explain it, Mateo. Why don't you go with the? I'll shut.
Yeah.
Up. Sorry.
Yeah,
I
it
shouldn't
will.
swear. I only swear on golf podcasts.
Yeah. So what ends up happening is that let's say you have a wind direction. Let's say it's going into the screen, right? The wind's heading into the screen this way. So what's going to happen is the wind is going to push this blade, okay, but in most positions on the right side here, and it's going to set it around counterclockwise just because of drag, okay? It's not very aerodynamic in that direction. The airfoil is designed really to move around counterclockwise, just like a regular airplane wing would, right? For example, if this one is heading straight into the wind, it has the least amount of drag out of any component in the system, and the others will have more, but in any position around the clock as you rotate, it's continuously changing. You have three of them. So you have a continuously changing coefficient of drag and coefficient of lift, basically, as it rotates around. Okay. Then because you do have an actual airfoil, there is a position when it's coming around the backside, basically the apparent wind direction, that you actually get a little bonus of some lift as it comes around, where the wind is actually increasing the force in the direction that it's also creating a torque. So the lift force is at certain points, the vector of the lift is actually going in the correct direction and creating a torque as well. So you have this combination of all these drags and lifts fighting against or not necessarily fighting against each other, but go with each other. So if you see like a regular anemometer that on like a weather station, you would see typically this would be a hollow hemisphere, right? You just have basically like a ball cup, right? You've all seen those. They make them really small and they use them to measure wind speed. So the round nose of this is the equivalent of the round nose of the cup, and the sharp edge of this would be the equivalent of the back end of the cup, right? So you're getting more drag from that. It's not aerodynamic. You're going to get more drag and you get less resistance on the nose, which would be this round surface. And then as it goes around, now on that system, you don't really get the benefit of any added lift. In this case, you get a little bonus every once in a while as it comes around a certain angle of the clock, basically. So that's roughly how that works, And people have done all sorts of different schemes. They'll use, kind of twisted blades that are more of a helical shape so that they basically smooth out the forces, because the forces are continuously changing. It's like a three-phase diagram, right? So you have three continuously changing phases of forces or torques that are rotating around, and by making it somewhat helical, you actually are extending across different a zone of angles rather than one specific angle, right? Because this is like a very discrete spot compared to on a helix. So kind of the general basis for this. So this is simple to manufacture. It can be made with a standard NACA airfoil design, which you know all the characteristics of. It can be fabricated out of aluminum and welded, and then we have a steel frame, hollow steel shaft, and then the main motor housing, which the motor in this case is a generator, acting as a generator.
Those are all to scale. That's what the lattice looks like.
Yes.
Yeah.
Correct.
The actual parts, they break out and
yeah, it's all bolt together. So these stubs are welded to the main shaft. So you have basically a positive connection socketed in here onto your main shaft, and then everything else is bracing to brace it for the rotational torque, and then some vertical as well, because we can't really rely. I mean, you could potentially rely on this for any vertical moment, but really wouldn't want to. So we have this vertical braced as well. So that's all just bolted together. And then because we're not socketed at the end connection and we have this lug basically coming out of the airfoil, we have two bolts there to take care of the fact that the force is not always, like an airplane wing, the force would always be in some lift direction, let's say to the right in this case, and be pulling on those. But in this case, it could be in any direction. So you're going to have a torque around that joint, which is why I have 2 bolts to take that. And they're pretty decent size there to make sure that we can take the torque without any fatigue issues. So, and then one of the things as far as the analysis goes is that you're looking at this in not only the rotational forces when it's active, what's going on there to generate basically your maximum power to your generator, mechanical power transmitted down to the shaft, but also at any given time. In particular, we look at the worst case scenario, which is if this was static and not rotating, but you did have a wind force in one direction in the worst case scenario, what would be that bending stress on this shaft, okay? And because it's continuously rotating, what happens is you have a continuous change in bending stress, okay? Because it's rotating while it's bent, okay? So we look at that.
What's the size of that shaft, just off the top of your head?
What's that?
What is the size of that shaft?
That's a 4-inch diameter. It's 4-inch diameter. It's 1/4-inch wall DOM tubing. So drawn over mandrel, seamless carbon steel. In this case, we basically have to make sure that stress is below basically a reversible, somewhat like a reversible stress. Then we can analyze it and look at fatigue on that. So, because this is obviously rotating around, so you have some number of cycles where if it was above a certain level of stress, eventually it would just snap off. So you could literally calculate it out to exactly how many revolutions at a certain stress it would snap. So then we have underneath the base plate, we've got this heavy duty chain coupler. So you can see here, double chain. You have a sprocket connected to an adapter shaft, which is machined here. And that's machined out of solid 4140. And that's bolted 2 bolts directly through. For some reason, it's not letting me show that. I was going to isolate that, but I can hide stuff easier here. So you can see the shaft as it disappears, right? We've got our bearings there, tapered roller bearings, top and bottom. Those are 6-inch diameter, 6-inch OD, 4-inch ID, tapered roller bearings. And then that's our shaft adapter. So we've got bolted with 2 3/4-inch bolts straight through the shaft, and then also a sleeve adapter on the other side to push up against the bearing, and then the key shaft down to the motor.
And that's a greasable chain bearing.
What's that?
Is that a greasable chain bearing? You can grease that chain and like it's got a bushing around it, or
The chain? No, it's an open chain. The chain here. Yeah. So
weather okay? Like, how do we get the?
Yeah, I mean it's sealed. I mean, you're not going to you'll never actually have it ever be submerged. As far as water getting into the system, the only way it could get in would be in a absolutely I don't even know, a really intense like high speed wind and rain event, or potentially.
Yeah, because that's basically its own motor housing, almost like it's.
Yeah,
we got those trap doors on there, but not trap doors.
Yeah, the doors on the side, and I'll show you, we have them out there. We have like a flange going around those, so you can't get any direct water, direct spray, so basically it's basically drip proof, or I'd call it like light wash down. It's not sealed, but you would have to spray pretty hard, at the right angle to get water to get inside, put it that way.
Would you caulk the top? You're saying maybe not, because it's just a
caulk. It's fully the whole top is welded so that it's waterproof. So, and then there's a cap on the top that also is like a drip cap that goes on the rotational part, this piece here. So this actually goes down over the big bushing so that nothing can get in through the top there as well. So
for the benefit of our listeners, Andrea is a mechanical engineer that will be very involved in project managing this as a subcontractor to Footprint Engineering. And Andrea, by all means, I'm sure you've got questions and you're just being polite and letting me do all the talking, but don't do that. What questions do you have as a mechanical guy? You're a P.Eng, Mateo's a mechanical.
Of course. Well, I mean, you're right. In a way, I was being polite, but you guys were asking really good questions, and I was just kind of absorbing it. I wanted to, confirm with Matteo. First of all, this was a very good demonstration, and the way you talked about the aerodynamics, it was quite clear. I wanted to ask about some of the stress stuff. Did you use like within SolidWorks, or did you use ANSYS or some other software to do some stress analysis to kind of test that out, or is it just kind of in terms of thickness and from your experience already overkill? So it kind of perhaps negates the
Yeah, so for all the parts of the actual, what I'll call the wind, mill side up top here, all of that we calculated out with just classic hand calculations, right?
Oh,
so we're using,
nice.
just write out the equations and put them in a spreadsheet and fill in the blanks. So even the aerodynamics and all that stuff, it's all resolved completely. So we have all of the dynamic movements of the aerodynamics resolving down to the horsepower of the generator so that everything matches, right? So we have to reconcile the wind forces at the anticipated average wind speed in the area and the size of the blade and the rotational speed and all these things that you want to have happen, and then dial that until it matches the correct horsepower, right? So yeah, I mean, I'm kind of
What is the average wind speed? This is the windiest place in Canada, by the way. I don't
Yeah, I think I can't recall exactly what it was. And Xander had put it all into the spreadsheet, but he looked up the average wind speed for the area just to get an idea, and then for the running speed. So
okay, that's good to hear, and that seems very extensive, and even that's like probably a better way to do it, because then you get the confidence that instead of just trusting a software, or at least you can do both, but
exactly.
What you did is even better, which is really fantastic. And
yeah, a lot of times I like to use the FEA. Like we obviously have Simulation Pro package in SolidWorks, which is pretty good. And but if you have to know what you're looking at, right? When you see pretty colors, everyone thinks that it's right, and pretty colors don't mean anything. So you really need to know what to ignore a lot of times in the stress analysis, or how to make a model that's ready for analysis to look at the areas that you already know are going to be problematic. That's what I usually look for in FEA. I'm looking for things that I cannot figure out, or I really am not in the mood for doing a week's worth of calculations like I did in my advanced strength and mechanics class, right?
Yeah.
So, at some point after being out of school long enough, you're like, let me find someone younger to do this for me, or unless I absolutely have to do it, I'm going to, break out the book and go through the whole thing. And that's why we have the software. And then obviously your experience comes in, and typically we know in some way, okay, what are we looking for? Where are the pitfalls? Where are the tripwires to look out for, and go in and target those areas, So, the main things are looking at, in this case, because you have a rotating system and a dynamic system, even to the extent, I mean, I kind of had to cut Xander off. I mean, if this had been, for example, if this was for GE, for example, like let's say I work for GE and we were designing a wind turbine, and it was some new system or something like that, the extent to where I would go with that, I mean, I have a list that just goes down to the floor of other things I would check, right? I'd be looking at resonance, all the different dynamic systems, the modes of vibration, right, on every single element, how all those things would input. But at some point, some of that stuff becomes you're talking about a huge amount of time, so a lot of times what you can do is you can do some really simple checks. You can say, okay, we know the approximate stiffness of the blade, for example, right? We know how long it is between these two nodes in the free length, and we can say, let's look at the first and second, mode of vibration, and run a quick calculation based on some generic shape, and say, okay, you know what, the resonant frequency, this might be somewhere in this range. Now we have 3 blades, so we have a harmonic, so multiply everything times 3, and just start going through that process and look to see, is anything maybe going to be a problem here, right? So, and a lot of times you're not able to do that. The time and the cost to do it can be pretty prohibitive. But again, it depends on the scope of the project. So.
Of course. And the GE things that you're mentioning, would they also be larger in size, or just kind of?
Yeah, for sure. And typically, like your conventional, horizontal shaft, right, on a 300-foot tower, big blades and things like that. So, and I think actually, the largest vertical, windmill in the world is actually in Canada, right? It's one that looks like I think it looks like a lemon. I can't remember the name of it, but I think it's huge. It's like 600 feet tall or something like that.
Oh, wow.
Yeah, I remember seeing it years ago when I was researching some stuff.
Mike, sorry, I just sorry to interrupt you there. I had Mike in the waiting room, Mike McLeod. You might remember Mike McLeod. He's handling Western Canada for our systems.
How you doing, Mike?
Good, thanks. How are you?
Good, thank you.
I think you were part of the Alexander one that Mateo didn't make. So we're letting Mateo do his stuff here. This is quite interesting, Mike. And
Yeah, you bet.
if you want to, we got Andrea, who's project manager that we're doing some subcontracting agreements with him. He's a P.Eng.
Meet you.
P.E. But no, P.Eng.
You could say P.Eng, and also for my name,
Andre.
whatever's easier for you, Andre or Andriy or Andrea, as you're saying, either one is fine.
Use Ukrainian, but we won't get into that politics. But he's certainly going through a lot with relatives over there and whatnot. So Mateo, for the purposes of Andrei, but also Mike, Mateo, go a little bit to your background and your masters and your business. I think it'd be probably good for everyone to use this video as a bit of an introduction to the fact that Mateo is going to be handling the US patent side for us.
Sure.
And he's happy to do it. And we think we can produce this product, Mike, now that we've gone through this exercise with Mateo. Go ahead, Mateo.
That's good.
Do a little bit of a 10,000-foot view of what you.
Yeah, sure. So, I mean, my background, I'm obviously a mechanical engineer, and that's what I was trained as. And I pretty early on in my career ended up getting involved with deep foundations and heavy equipment, geotechnical, geostructural, and structural engineering, and a lot of work in the field, out boots on the ground, solving problems, running work. Very complicated, logistically, basically nightmare drilling jobs for foundation drilling in the city, and then other projects that were complicated. And those are the ones that I like to do. I like to do things that are really challenging because I enjoy that grind of the problem solving part of these projects. So, you fast forward years later, and I still do some things to do with drilling tools, heavy equipment, mining, and other things like that, cranes, hoisting, and all those things. But I also do a lot of more high-tech electromechanical and mechanical design and manufacturing, full service design manufacturing. So anything from design and design build or design only, from consumer products, military, aerospace, defense, microelectronics, assembly, packaging, inspection equipment. I have patents on inspection equipment used in all sorts of different, high reliability military electronic systems. And some of our work is also just build to print. So we have low volume, high value added manufacturing projects that most machine shops and shops don't really want to get involved with, or they have too many facets outside of their normal comfort zone or their expertise to really handle. So someone may say, oh, well, this job is 50% machining and 10% of 5 other things. And if you go to a machine shop, they're like, well, I'll do that, but I really don't want to do this other stuff, right? I don't even know what that is. I don't even know what you're talking about. And it's a turnoff for a lot of customers because a lot of people are looking for turnkey, right? So they're just looking for just one-stop shopping. They just want to call me and say, here's what I need done. Here's all the stuff. Just figure it out. Just handle the whole thing. Like, I don't need to know. I don't care if you're doing it or you have 5 other people doing it with you. They're just like, we just want to come and have you just handle it. You distribute it on the back end, however you need to do it to get it done. So I'm transparent about that. I mean, my clients know my resources spread out way beyond what we have here internally to be able to accommodate that. And they realize the benefit of that, because most places look at that as a weakness, but I look at it as a strength. It's like, I already have the capability to do a ridiculous amount of things here, way beyond what any typical machine shop would have, right? So we have everything to be able to prototype almost anything you want on a day's notice, other than just maybe having some specific raw materials. So we have everything from CNC machining, from turning to milling, water jet welding, all the different welding processes, other sheet metal fabrication, tons of hardware in stock. So anything that's within the scope of our typical things we deal with, we have everything here. So all the hardware, all the little things that you're not going to track down and find at Lowe's or Home Depot on a Saturday night or something like that. And then the ability to obviously do real design, real engineering, and work on things that are just not really simple, right? So that's really where my expertise has come, is just just a general, almost a generalist approach to problem solving and design and manufacturing. One of my friends who's worked for P&G for almost 20 years, he I saw him the other day, and he said, he goes, I refer people over to you all the time. He said, he told someone the other day, he said, oh, just call this guy. He goes, he will literally design anything you want and make it. He was just like that. He goes, I don't have anything else to say. He's like, just whatever you want. And I'm like, and it's true. I mean, there are some times when I'm like, maybe I don't want to get involved, or it's outside of the scope, or, there's no way we could actually handle it. It might be too big, because I do have access to some of the biggest and best customers in the world. So at some point you have to figure out where to focus a little bit. But for me, I enjoy, and we like doing, a diversity of different types of projects and getting involved at all different types of levels, and just meeting the clients where they need us. And instead of saying, well, this is what we do, take it or leave it, it's more of a, what do you need? And, okay, let me figure it out. And this is how much it's going to cost you. And if those two work together, then we're happy to do it. And sometimes it's not really about the money. In some cases, like, there may be strategic projects where we look at it and say, okay, well, someone's going to give us, it's not necessarily just a challenge, but sometimes it's an opportunity to learn something new or get into a field that we haven't been able to get into. And there are definitely roadblocks to work for certain types of organizations. So when you're getting into aerospace, defense, military, and certain other areas, it's very hard to get in. And, you can't solicit these companies for work. So you have to figure out other ways to get the business. And typically that's through referrals and all these other jumping through a lot of other hoops. So in many cases, we're biding our time and working on these strategic projects to show that we can do certain things in an area where eventually, if you wait long enough, 2, 3, 4 years later, all of a sudden the stuff will come back full circle, and we'll say, oh, these guys are actually really good at that, and then you'll start getting, in my case, we'll get emails and calls looking for very specific things in industries where, like, I don't even know if anyone else even does it at this point, so other people will fade out of it, and we'll come in. We look at those as opportunities to make some standard product for industries where once they put it in their system, they'll use it forever as a tool. So a lot of that is tooling and things like that used in electronics manufacturing for defense. So and then everything, 3D printing and all the other cool stuff, pretty much a little bit of everything. We get at this point, even Xander, when he came and started working here, he said, I finally realized that it's not, do we have one of those, but where is it? Because he'd ask and I'd say, oh yeah, it's over there in that closet, or it's upstairs, or it's back in the mezzanine or whatever. And he just realized, he's like, you literally have one of everything. So all the little widgets and the gazintas and gazantas, all those things. So, and that's fun, it's exciting. And, we get involved with a lot of interesting projects that literally no one else wants to do. Like, no one will do it. I have things that we've had to make where we've tried to get other people to make them for us, and you just can't. Eventually you just get up against the wall. You're up against the wall, and the schedule is rolling continuously, and eventually you get to that at a point where you're like, I can't wait any longer. I'm just gonna have to figure it out. Right? You start making these exotic things. So
and then you do some part-time professor work.
Yep. Yeah. So I teach. So I'm starting next semester. I'm fading out of the thermofluids side that I was teaching this is my third year doing that. So fluid flow and heat transfer, experimentation and things like that. And now I'm phasing more into the manufacturing and the design side of things. So the manufacturing labs, which is where we're doing like quality assurance, inspection, actual machinability processes, things like that. And then over time, I'll get involved and try to see if I can, basically try to use, let the university and the College of Engineering at my university to be able to use me as a tool as an advantage to them to use my expertise, which is how they should be using everyone who is, there, right? As you find what their expertise is and how can you leverage that, combine that to make sure the students are getting the best experience. So that's my main goal there. Is obviously it's a nice, it's definitely a nice gig for me, but when I'm there, I'm always looking at it as like other students getting what they should be getting here. I always think back to what I learned when I was a student and how the professors went about presenting that information and how it tied together in the progression of it. And then sometimes I kind of take a step back and say, okay, like, what am I seeing here with my students? Are they getting the same experience? And how can I get it so that they can get what I would consider to be the best possible experience here, so whatever I can do for that. So I do enjoy teaching for sure.
So then the Hub Foundations thing, we think that they might even put one of these in, Mike, because they could put one in their yard, which is, I poked GFL to say, just put it in your yard. Right?
Yeah.
Throw one in because you got drill rigs there and liners and whatnot.
Yep.
So what we're covering,
Yeah.
show them that 3D picture because Mike didn't see it. If you could just
Sure.
put that up again, and then we should go on the plant walk, I guess.
Yeah, sure. Yeah, so you can see here, I can unhide the rest of the goodies here. Yeah, I mean, for a drilling company, it's no brainer because, one of the biggest expenses for a company that is not a drilling company is getting someone from a drilling company to show up, right? So if you already have the drill rig, and you're in your own yard, you just wait till 3 or 4 guys are there for a couple of days, put in a shaft, do the rest of it whenever you get around to it. So, but it's always easy to throw a casing in the ground and plug the bottom, right? Prep it out and get it ready to go, and then do the top work and everything else later. So I think it's a no-brainer for drilling companies to be able to put these in their own yards. And depending on what they are looking for on the geothermal side, obviously they could put one or multiple wind towers up, but that doesn't need to coincide with the exact number of the FeBTU cells, right? So you could definitely put more of these if they wanted more capacity, obviously spread out, right, to accommodate not overheating or overcooling in the ground, things like that. And depends obviously on the exact situation, but for sure they could do a little, these anywhere they want, and then have a couple towers. So
we believe this is the best dry ground geothermal in the world. It has an overflow, and I don't think you have the detailed drawing. You just have this drawing, eh? In terms
yeah, just the model. Yeah, we'll generate a drawing from this, showing the whole scheme.
So Mike, that comes 48, 72, 120 inch outer casing, 20 and 24 inch inner. The inner is running through a water furnace, which is a water heat pump. And nice thing about this is you can have short lines to, you can put a monopole next to a building and structurally, and then that's what we have here in the Feng office in Godrich. So we're testing the full system, and Mateo's going to ship this next week. We're going to do a walk around in the plant.
Yeah.
Now, I guess if you're
Yeah,
good
I can do
to
that
go
now.
to-
Yeah. So let me just, I'm going to mute this computer.
All right, how's that? Get that. Okay, get the speaker off there. Good. Okay, so yeah, so we'll walk out here, switch my camera around. So you can see, so here's the top plate where the bearings go, right? So we've got our top bearing here, and obviously you can't see it from the bottom there, but that's the main top plate for the motor housing. And these are the door covers.
Mike,
for
we
the
did get a
sides.
finished paint job out of this guy. So in the end, I didn't want to have to paint it, but Mateo suggested, what do you got for paint on this now, Mateo?
It's an oil-based industrial paint, so it's just brushed and rolled on, 2 primer and then 2 coats of top coat. So it's pretty heavy duty. And this is the motor mount. So you can see we have the for the motor, we have the ability to with the slotted holes all in different directions, so that when you go to put the motor on, you have plenty of movement in every direction to align it, to get the shafts aligned, because we don't have the physical motor here. So we're going off of obviously the 3D model, but that gives you plenty of room. You have basically an inch in every direction to move around from the theoretical position. So, and then this is the main housing. So you get your attachment to the pole on the bottom flange there, and top flange and everything else. So you can see he's welding on one of the foils now there.
So is that your last blade?
Yeah, that's the last one. There's a little more work. So but with this particular welding, you have to run, there's basically different techniques for each gauge thickness. And when you get down to the thinner gauges, it becomes a little tricky. So we have a Muller 350P high frequency pulse welder that is probably one of the only ways you can weld anything below 1/8 inch in aluminum in like large scale without TIG welding, which obviously would take, hundreds of hours to TIG weld the entire thing. So in this case, we're using that for the thin gauge stuff. And then we have to change the settings for each different component on the foil. So all the big fillet welds and things like that have to use a different technique, because fillet welds on aluminum are extremely problematic. Even TIG welding, they're one of the hardest welds there is. So, but you can see here all the link plates and everything like that, right? So you can see the connection just for scale size, right? You can see how big this is, right? So this bolts directly to the lugs coming off of the foil, and then your braces connect here. So that's the vertical brace, and then the lateral braces that connect to basically a triangle. So, and a couple of the caps that go around the main shaft for through bolting and stopping the shaft on the bearings. And then you can see here, right, the lugs for the connection and the foil. So these are bump formed, so they're not continuously formed. They're bent in a progression at specific angles at specific distances to get basically the approximation, pretty good approximation of what that NACA airfoil would be, right? So you can see they clean up pretty good. So it's definitely a different, approach and process, but to be able to make this in this method, this is probably one of the better ways of doing it. So, and then you can see just some of the other equipment, right? So we have turning centers, lathes here, more welding equipment over here, and water jet, so you can see, we can cut on this up to basically anything, whatever you can fit under the nozzle, but you can see even this is 3.5 inch thick aluminum plate, which we can cut. You can see even like that, like a 1 inch hole through 3.5 inch plate with just abrasive and 45,000 PSI high pressure. So, and then we've got milling over here. So he's running some stainless steel stuff over here, and there's some engraving and other parts going on over there. So and you can see, other stuff like this we're doing, full penetration, kind of complicated. These are all fully machined and then welded together, full penetration welds for an abrasive blasting system. So there's an auger inside of that, things like that. That again, most places are not, we even have an oven for heat treating. But there are a lot of things we get in that are just not, other companies are just like, maybe they could do it, but a lot of times they're just like, what, I just don't want to change up what I'm working on, and I'd rather not. So they just kind of punt this and kick the stuff down the road, and eventually we end up doing it. So
Mateo, I've got two 15-horse high pole magnet motors installed, and that would be a 5 kilowatt according to Chad Armstrong from Windworks, who's done it before. And he was the one who, there's some nice video of him putting the magnets in that I took in my previous show.
Right.
But what would be, in your opinion, the lead time on what we've just gone over in terms of if you were to get an order, would it be a couple months to generate something like that? Or could
No, now that
one order a week, could you do 4 a month?
Yeah, I think it's doable, because what we would do is, now that we know the process and we've debugged, so obviously in the first one, you're always, you have a plan, you make your drawings and you go through, and your prototype, you're always going to have your however you're going to get that to the point where eventually you're going to have basically some sort of a Rev A type package at the end, right? So we go through and we say, okay, this is how we plan on doing it. And then you say, well, this didn't really work so well, or we didn't want to do this, or we decided, for example, we changed the motor mounting scheme later on because we really realized that it would be a lot easier to just mount the entire motor up to that top plate, so that you have one mechanical assembly to align the shafts. It just makes sense, where before we're thinking more serviceability, but you can pull the motor out in a different way, but it's much better this way. So we changed that somewhat on the fly just to make it. And that's the thing, is like, you can't be afraid to be like, what, there's a better way of doing this. Just stop, and just do it the right way. So we changed that scheme there. But I would say realistically, even the welding is on just the blades is at least a week of just someone welding, fitting and tacking, and then welding on the blades. So But that doesn't necessarily mean that the same person has to do everything, right? So they can be split up. The steel welding is different from the aluminum welding. It can be done by two different people at the same time. So between that, by the time you get an order, it takes basically a week to get all your raw material in, flame cut plates, things like that, your non-typical stock. So you're looking at basically a three to 4 week lead time, ARO for a random order off, kind of just coming in off the cuff.
Andrea, you must have some questions. I want to give you a chance to keep asking good questions. Mateo's going to be a good mentor if you can ask some questions on this process.
Yeah, of course. I mean, I had a few that were slightly more general at the beginning. I mean, what I found intriguing at one point was that you're quite experienced with a lot of different things, and I'm very excited to potentially, as I'm working with Martin and Mateo, so I can learn a bit more with some of the projects that you're doing. It's interesting that you're kind of, the thermal fluid side is one of the sides that you're kind of moving away from, most heavily involved with over the past 6 years. So I think that there's some potential for synergy in that way. And of course, there's a lot of thermodynamic related stuff and thermal fluids that I would love to learn more about that. I wanted to ask, what do you foresee this system, the wind turbine and perhaps the turbine combo with the ground source connection and other things? What do you kind of see? First of all, what's the power output in terms of megawatts or in that range, or gigawatts? Well, not one perhaps, but and what do you foresee as far as the implementation across Canada and US, and how long do you think it would take to get, let's say, 100 of them or 1,000 of them in terms of large scale efficacy across North America? Or if that's even the goal, because again, I mean, I'm kind of jumping into this meeting with not that much information, but that is partly on me because I was busy for the past 2 weeks, but I'm doing a lot of catch up today and yesterday. So
those are good questions, Andrea. I think, at some point in time, Mateo would be bored with it. So he'd have his drawings, we'd prove concept on 5 and make some money maybe next year. But I think probably, people would tend to make those things on a subcontract basis, I would think, if there was QA. Would you agree, Mateo?
Yeah, for sure. I mean, and that's, and we have, for example, like even the welding, right? We would do the first one, we might do the second one. And then at some point, I've got 4 or 5 professional welders within, literally 2,000 feet of my shop that I can just say, hey, would you like to weld these, 1 a month? Here you go. And it will cost less than what it costs us to do it. You know what I mean? Because we're charging the most, like we're at the highest level because of the nature of this business, right? It's not a guy with a welder in the back of his truck in a welding shop with a bandsaw and 2 welding machines. We've got $1 million worth of equipment sitting in here, and $250,000 worth of inspection equipment and $150,000 in software. So, in order to even just show up and turn the lights on here, it's extremely, the cost to just exist is very high. So that's why it doesn't really necessarily make sense. Once it gets to the point where it becomes like you just doing the commoditized process, we debug it, we figure it out, we say, okay, here's the process. You're going to use this welder, or you're going to come over and weld this in my shop with this welder because you don't even have one. Use this machine. Here's the parameters. We tacked it up. You burn wire for 2 days. That's a lot of times how we'll do it. So, and we have people who work with us like that, right? So they like that because they also it limits the part that they have the hardest time with as like a fabricator, for example, which is dealing with CAD, interpreting drawings, right? Specifications, all those other things, right? We can just say, okay, we've already dealt with all that stuff. You just do what you do, So at some point, yeah, you do move towards basically a distributed manufacturing scheme, which is basically using subcontractors it's kind of vertically integrated, but it's distributed manufacturing. And I think that, with these types of things, like when you look at power distribution, one of the issues that I see, and I'm involved with a lot of hydrogen related technology and some other things that are coming up down the pipeline. So I've had a lot of conversations with a lot of big companies on hydrogen storage, transport, liquid hydrogen, fuel cells, and things like that. And one of the things that everyone's always looking for, this like end all be all solution for like massive grid scale clean power distribution. And a couple of things. One is people use too much power in general, right? That's a problem. Just for whatever reason. I mean, it just is what it is. You know, we all in general using too much, you know, power, too many resources, too much of everything. Like we've gotten spoiled, and you know, basically we've been spoiled. Okay, let's put it that way. If you go back 100 to 200 years ago, I live in an old farmhouse. It's from 1790. You know, if you go back to the time when they built that house, you know, when winter came, I mean, you were hungry till March. You know, you know, so we take for granted that we can just go and I can just go get to an Italian restaurant and get enough food to, you know, feed a town on one plate. So I think in some cases it comes down to people's lifestyles and trying to figure out, like, you know, I mean, it's not a bad thing to have nice things and to do these things, but to do, like anything, everything in moderation, right? Not over consume. And then creating power at a higher density in local small communities. So, I mean, even 10 or 15 years ago, I was looking at the idea of making basically micro power plants in developments of 1,000 homes or less, you know, ideas like that, right? So when you start talking about like distributing power with a system like this over a large scale, when I think of that, I think of more of a large scale being like, you know, how could you do that for a relatively small community that makes that community basically self-sufficient in some way or less reliant on these outside resources, you know? And simple things like this, right? It's relatively simple. There's not that much material involved. You're using a commodity, which is you know, an induction motor, but modified in a way, obviously, that we're doing, right? So it's relatively accessible. You don't need to go to make the motor and to make these things. You don't need to do anything where you're relying on, for example, like, you know, rare earth materials and all these other things that are really nasty to process. You know, aluminum, steel, relatively simple. And then you try to reduce the amount of that. So even optimizing the design to reduce the actual amount of the total weight of steel, because making steel obviously is also a consumer, right? I like the idea of trying to implement these, you know, smaller scale power. And there's so many opportunities for that, but I feel like everyone's just always going after these big, you know, oh, we need to give power to everyone. We want to make it all green. And, you know, the big push lately has just been batteries, and there's not enough power to charge all the batteries. So it's not even doable. You know, when you run the numbers and you hear these people break down how much power it really takes to be able to charge, you know, 2 Teslas in your house plus your batteries if the sun wasn't out because your solar's not charging, plus, and you realize it's 4 times as much as your daily consumption of your typical household usage. And you start going, well, what happens when everyone has that? And then they're trying to mandate that stuff. So I'm not even getting into any political part of that. It's just literally a matter of just numbers. You just take, you know, no one wants to just take numbers and put it in a spreadsheet and just look at the bottom line without kind of just giving their opinion. It's like, well, what's the number? You know, then we'll talk about it. So there was an instance recently in Florida where the hurricane a couple weeks back, where there was a community that had, you know, it probably was an HOA, you know, style, like a master plan community where they had planned and they had, I think it was mostly solar and battery backup within their community. And I don't know how many homes were part of it, but they were able to basically have no power issues and were perfectly fine after the whole, you know, western side of the state was just wiped out, right? So, so you can see where I think people get nervous. It's a very, like, definitely a very American, and I feel like maybe potentially just a Western thing in general of like, I want my own stuff, you know, I want my own well, I want my own power, and it gets a little tricky when you start sharing, but I do think that in a lot, there's some states, and I'm sure it's like this in Canada as well, but some states in the United States where it's a little more common to have these kind of what are called master plan communities. And those are the areas where I think that if they plan it in advance, they can try to control a little bit more of their own power, right? Their own consumption. And you know, you need people who are going to put the time in, and sometimes, you know, and just want to kind of do it almost for fun, because these are kind of interesting projects, and figure out what that means for that region. And every region is going to be different. Every region has different environmental factors. Some may have more sun, some may have wind, some may have the opportunity for hydroelectric or all these other things, right? So there's so many different opportunities, and so I don't know. I mean, it's a convoluted, long answer to a simple question, but it's something that there is no just answer, right? It's
Let's
more of a
talk-
discussion.
Hey, sorry to interrupt you. But that was very good, Mateo. I think basically that you've done what we asked you to do there. Let's talk about our business deal. So, I think this is okay to record. Mateo's going to represent our patents with his background. He understands them all. And we're going to kind of do a 50-50 with him. So we take a top line and we're looking to make it quite reasonable because we don't have to make stuff for the patents. He can choose
Right.
this or not make this on the end. But the FeBTUcell, that'll be bought and put in with caisson drills, right? And most
Right.
of the patents are geotechnical. So he's looked at them. I think you printed a set of the
Yep.
stuff, and we continue to improve our marketing to have a word, like an explanation. Mike helped us on the FeBTUcell because you have a drawing and it's not necessarily understood exactly what's in my mind all the time. And what I think is going to happen and why I think it's going to happen. We believe that we'll have the highest return geothermal in the world. And it's a magic water table, but it causes an overflow and evaporative cooling on the outside. So, how quickly can we make headway? We're looking at maybe letting someone try it for $5,000, Mike, but the basic price is $25,000 US with 5-year license. And we're thinking of, Mateo and I are thinking like 100-mile radius around the city. So he was going to offer that to Hub Foundations, who he used to work for. He knows them well. They have a lot of confidence in what he might endorse. So why don't we try, my podcast guy thought we should try to do a podcast just on Mateo and then our business deal, but I'm going to try and capture it here for the
Sure.
benefit of people listening. So what's your thoughts on that, Mateo? It's going to be easier than doing machining, I think.
Yeah, exactly. I mean, everything has its challenge, obviously, right? They're all always different. It's just, different, it comes at you in a different form. So, but I think the biggest thing is finding, and we talked about this, I think, a couple of weeks ago, where it's like, who has the biggest opportunity to be able to implement these types of systems? So so for example, for the FeBTUcell, for the geothermal side of it, and anything that involves, using a caisson rig or, a hydraulic drill rig to install large diameter pile or casing, the ease of use is basically goes to a foundation drilling contractor. Or we also talked about like the developers, right? The big developers they're putting up buildings, they have control over the entire design, they are working with the owner, and they're looking at what ways they can get some of these benefits of energy savings and reducing consumption, things like that. And I think one of the opportunities is to actually solicit a little bit, not only to the drillers, because they can become more common here, but it's still not really common enough, where the geotechnical engineers and the builders are going to a foundation contractor early on and saying, here's what we're thinking, and you're early enough on to say, hey, well, while you're doing that, why don't we put some of these over around the perimeter, or put them underneath at the bottom of the top down job, right in the bottom of the, down 6 floors, put the cutoff down even further, and just fill the basement underneath with these open loop geothermal systems. Obviously there you've got, head pressure and things that you'd have to deal with, because you're probably gonna have some artesian issues, but in some cases. But what happens is it's always the 11th hour, we put the job out to bid. We don't tell anyone anything more than they need to know. We go with the lowest bidder, and, you show up on the job and the foundation contractor shows up. And by the time everyone maybe realizes it was a good idea, they're already done and they're already putting steel up on the building. So it's just too late. So I think a lot of it really comes down to letting the builders know, who are developing the property and have control over the situation early, let them know, hey, like, tip them off. Here's something you can do if you're putting in drilled shafts already paid the mobilization cost, which is the biggest cost of the whole thing, right? Putting in a 4-foot diameter piece of casing down 40, 50 feet almost costs nothing if you've already paid for the mob cost. So they're already paying that. While the guy's there, have them drill in some more cans, leave them down deep, cut them off when you get down to do whatever you're going to do. and go in and do the rest. So that's just on the geothermal side. I think to get them underneath actual buildings in the city, and not as a foundation pile. Obviously, it'd be separate because we don't want to tie up, try to deal with the structural part of it with that, because it can be an issue, but figure out where to put those. So I think that's the challenge on the geothermal, is just letting people know early enough on to even realize that they can put it in and then plan around it. On some of the other ones, like I've already spoken to some people who are involved with, like the major potable water systems in the greater Boston area, and about some of the other, like the repair systems, like for the corrugated metal pipe and things like that, right? And they were very interested, thought it was really had some serious potential. So we're going to look at doing potentially like a case study, right? Where you say, okay, let's, without even doing it on a real, because, you take something like that, you say, well, great, you have a technology, but you have to try and test it within the scope of the specific organization. Like I remember when I first got involved with foundation drilling, micropiles had never been used on an actual Massachusetts Department of Transportation bridge before. So when I was with Hub, we did the first job that ever used micropiles as the foundation for a bridge that was made or was part of a Mass Department of Transportation job. And that's how it always is. It's like, well, everyone knows micropiles are great. They've been around forever, but no one had ever gotten into that point where they got everyone on board to say, yeah, it's good enough. We've done enough testing. You've done the test on the job, and check off those 100 boxes or so that, and the people who are naysayers and just don't really care about progress. They just want to show up and just do what they did yesterday, and they don't want to innovate. So getting in with the engineers who are like, oh, you know what, this could save us. That's the real thing, is you want to say to these people, how much can it really save you, in the long run? Can you repair this pipe in place? For example, when we're talking about water mains, and some of these in our area are 10 foot and 12 foot in diameter, and they're going really far to feed, for example, city of Boston. So you have all these different situations, and it's like, well, just do some tests, torture tests and stuff, prove it out, let them prove it out, get a contractor that they know, that they trust, to do the installation, and you do a small trial on a small pipe. They do their whole thing, and then you say, okay, yeah, let's try it on, a real job, but in a place where maybe it's not super critical, right? And you tiptoe your way into it, and eventually it just becomes normal, right? And then they say, hey, you know what? We're just going to use that as the typical repair in every situation that's like that, no matter what diameter, no matter size, no matter which application. So a lot of times it's not just about advertising and marketing. It's getting engineers on board, getting people who actually they're looking for something interesting to do, to innovate, things like that. So I think that becomes the fun part of it, right? Is the scheming, right? And is just getting together with people who are like-minded and say, hey, I get this particular technology, particular process, how do you, not saying this is how you apply it, but be like, how do you think you could apply it with the stuff you're already doing, right? And then figure out a way that they can use it, and then a way they can use it where they like it and they're making their customer look happy or look good, right? Everyone likes to look like a hero, right? So you keep passing that to the next guy and say, hey, I'll make you look like a hero. You make your client look like a hero, and everyone's like, hey, this is great. Hopefully it ends up being good for everyone, and then it can be implemented in other places. I think all these other, the whole suite of, IP is all, relatively geotechnical, geostructural stuff. So it's a very similar cast of characters would be involved. And
I was going to summarize, just for the benefit of people listening that may listen to this over and over a little bit, the costs, you save a lot of costs when you try to lower CO2, and whether it's energy or the concrete and steel equation, which Mike's intimate with, we believe we're going to save people a lot of money. So the owners hopefully get a good chunk of that. They can even get licensed and hire contractors, or the contractor really, who we know well, Mateo and I and Mike, we're looking for them to do design build and to have detailed designers that would, get a comfort level with what we believe is true value engineering. We're not going to do the detailed engineering. I said to Mateo, other than any windmills he wants to take on, but other than that, really, we want to avoid that and make a difference in the built environment where there's a lot of footprint. So, and we have these patents for 20 years. So I don't know whether we'll do any more, Mike, but we probably between Mateo and I and maybe you, we could be a bit of a run here. So I keep saying I'm going to stop, and then I think of something, Mateo, and I try to get a patent paid for.
Yeah,
So
I know what you mean.
Mike, we unmuted you. If you have any questions, you always have some good ones. But
So the first question I have, and this is really, really interesting, and I must have missed a little bit of the beginning while I was waiting to get connected up here. But so you're located where in the world, Mateo?
I'm in Massachusetts, just north
You're
of
in
Boston.
Massachusetts. Okay,
Yes.
all right. So have you got this in place? Like, is there one in the ground already?
So the first one is at Martin's property, right? And what is it? It's Godric.
yeah, Godrich.
Okay, so that's
yeah.
the one that I've seen pictures of. Okay.
Yep.
So the
Yeah.
monopole comes out, we just got to put the top on. So this
Okay.
is on it. And maybe you can describe a little bit how you visualize that, because he's going to ship it to me. We're going to have a Feng logo on it, but
Yep.
it's his idea. Then the idea would be we just rig it, put it up and bolt it on, Mike. And then
Wow.
Yeah.
the like we're 10 kilowatt. So on this 30 horsepower motor with those magnets. So I don't know what that is, 4 watt or 6 watt hot or whatever they call it. So that comes right down. And talk about we're still going to try and get a dog on it and a brake on it, eh, Mateo?
I've been bouncing around some different ideas, and obviously on the prototype stage, you get flexibility, but I think in the long term, not only for the lock and for a friction brake, we're most likely going to end up just implementing I wanted to try to do, but they don't really make them large. We could potentially, you don't want to really make something that's already a commodity, right? So you just make it for 10 times as much as you can buy it for. So I was looking at brake calipers, right, to just basically put a disc brake on the system, because obviously you can brake with the motor if you have a controller that will engage it to do the braking. But if that's not built into your motor system or your generator system, then you can't just engage a brake. You can do reverse it and load it up. So the idea is basically to put a disc in the system and use a hydraulic brake caliper to just squeeze on a rotor. So we most likely in that case would end up using. I don't think we necessarily need to go to a automobile size. We're going to look at the torque and the loads, but most likely basically a high quality motorcycle caliper. Very easy to implement. There's pretty much anything you can imagine for basically maybe about $100. You have a steel disc that's on the main shaft of the motor directly connected, and that can be mounted right on the motor housing. And then you just have basically a brake line running down the side all the way to the bottom and a master cylinder. Now at that point, all you do is you have a master cylinder hooked up with like an over center device, and it would just basically a handle. You just pull it down, and it would just engage the hydraulic pressure with the master cylinder, engage the brake. So if you wanted to lock it in place and make it so it can't spin, you just pull it down and pin it in place. And if you just need to, basically engage the brake, you would just pull down and you could slow it down. But you do it from the ground, And obviously this stuff could be done electronically. You could just you can do an electronic brake, but still use hydraulics as your main actuator. So if you needed a remote braking or something like that, or like an overspeed, right? So depending on the situation, someone would say, well, you know what, I really want to be able to, I don't want to have to go out there and look at it. If it's this particular situation, I want to just lock up certain times of day or certain seasons. So if the wind is over a certain speed, I want the brake to engage and stay engaged, right? You put a couple sensors up there, and now there's so many, with electronics and all the Internet of Things devices, it's absolutely unbelievable what you can get for a couple $100 for data logging and controllers and things like that. I just built an earth sheltered greenhouse, and I mean the little IoT data logger with the sensors, and then also a separate controller that controls fans, heat, cooling, humidity, and everything all packaged up in one. between the two of them is only like $300. I mean, it's like amazing, you know. Now you're talking about a small greenhouse, but these things can be, you know, used in larger units as well. But it's just amazing, you know. I mean, you know, if you wanted to do that before, you know, every piece of technology could just fit in your hand for a consumer product, you're talking about just thousands and thousands of dollars, right? So you can easily monitor, you know, the wind, the temperature, the light, all these other things, and just basically have a very small PLC just saying, hey, you know what, engage the brake, do this, do that, turn that off, turn that off. You know, no big deal, you know. These are like commonplace things now. So it's pretty impressive.
Do you think we could get something like a vertical pin just to dog it?
Yeah, for sure. We're definitely going to do a mechanical, like a single mechanical pin lock. Yeah, just a drop in. Yeah, we'll just use like a 1-inch diameter, like a class 2, you know, like for a tractor, you know. That way anyone can get it at Tractor Supply, you know, or the local farm supply. Drop a 6-inch long, you know, 1-inch pin in there. So, but yeah, basically we have 2 picking points on that main top piece, 2 pad eyes that are welded on there. So you can pick it up with 2 shackles and 15-foot spreaders, fully assemble the whole thing on the ground, pick it up, put it up, and just bolt it with 8 bolts right to the flange. And really, if you wanted, you could even, you know, potentially, depending on the hole clearances, you know, we could even make it so that as far as assembly goes, instead of them being through bolted, we could even weld that, you know, do a little stitch welds on the head of the bolt so they're facing down like studs. So when you put it on, you don't even need to open the sides up, you know, but you need to field wire it anyway. So, you know, if you're already going to be up there wire it, you're going to need to take the doors off and things anyway. So go up there, a wrench and you know, a couple wrenches and bolt the thing up.
Part naming, give us a packing slip with the part names and numbers.
Yeah.
You're going to
Yeah, we'll give you a drawing with a balloons drawing, you know, and then we'll just number everything. So, and there's no, everything's symmetric, you know, so the parts, you know, there's no right-handed or left-handed parts, you know, or, you know, it's all interchangeable, you know, so that's a typical design for manufacturing thing, is just don't make more unique parts than you need to, you know. So
can I ask a couple questions on risks? Like here in Southern Alberta, we have a lot of windmills, and they're the large, I don't know, they must be like 300-foot diameter. They talk a lot about, I don't know if it's called energy fields, or, you know, so that you may be affected within a certain distance of a windmill for maybe sound or for high frequency. Is there anything with this design you think that could be affected with those kind of considerations?
Yeah, I mean, anything. I mean, it depends, you know, on where you are, what's around, and, you know, and I think it always depends on what's happening at the time. I think in different times of year, depending on the ambient noise and ambient light, you'll notice different things. So it, you know, may be annoying, you know, where sometimes they may not, or to an animal they may pose a problem, and some other times it may not. So it just depends on how those things overlap, you know. I notice sometimes where you hear, you know, a certain sound, right, where it's drowned out by something else typically, but then all of a sudden that other sound that is kind of drowning it out is gone, and you're like, well, what is that annoying noise? But it was always there to begin with, right? So yeah, for sure, you know, there's always going to be a risk of some odd, you know, frequency, you know, where people are like, oh my God, turn that off, you know. And I know it happens for sure. I know with the large ones, because the blades are so big, you end up with, depending on the trajectory of the sun and houses, they will have flicker issues, right? So you get the frequencies very close to the natural frequencies that are running in like your brain waves and things like that, right? Very low, 4 to like 8 hertz. So you'll get this flickering, and it can cause seizures. So like people will literally be washing their dishes, you know, the sun's coming up behind the blade, and next thing you know, they're on the floor, right? They have some reaction to that, and obviously that doesn't happen to everyone. Different people have different sensitivities to that stuff, but that definitely happens, and they'll, depending on where it is, and those are huge, so they have a much bigger effect. Smaller the scale, the less effect it's going to have on, you know, the amplitude of any noise will be lower, even if it was actually does make noise. Theoretically, the amplitude would be smaller because it's not as large in scale. If there was a flicker issue, it would be this is much lower to the ground and smaller. So for the light to come through, depending on what that hits, and if you're in an industrial area or if it's in someone's, yard or something like that, they're not going to be too worried about it. But it's usually when with your neighbors, right? So if you, for example, you're going to put it up on your property, but now you have neighbors, right? You have to ask, you got to be, conscientious of the fact that you could cause an issue for sure, So I think that, something where we would probably want to make people aware of it when they're siting, right? Say, hey, these are potential things you may want to consider. Do you have any? Is there anyone right on the other side of your property line? Are you putting this 30 feet off your property line, and your neighbor's house is right there? Are they going to be? You're going to make a bad neighbor out of it or something like that?
It'd be good for farms and close to the
Yeah.
house to make the
Yeah, for sure.
the inputted energy low on the water flow.
Yep.
I think
How
I'll
close?
cut off the recording. Thanks, Mateo. And we can keep talking, but I'm going to cut off the recording and
Okay.